In April 2026, the World Meteorological Organization issued a stark warning. Deep in the equatorial Pacific, ocean temperatures were rapidly rising, signaling the imminent arrival of a massive atmospheric disruption. This chart tracks the probability of that disruption. Notice how the forecast curves spike drastically by mid-year, indicating an 88 to 94% chance that this event will dictate global weather patterns by the end of 2026. To understand why this specific forecast has global governments and agricultural markets on edge, we first have to look at how the Earth's climate system operates under normal conditions. This phenomenon, known as El Niño, is Earth's master weather maker, a single oceanic shift that dictates the climate patterns of the entire planet. The Pacific Ocean is Earth's largest heat engine. It receives more sunlight than any other region on the planet, storing immense amounts of thermal energy in a highly delicate physical balance. In this Pacific cross-section, steady easterly trade winds blow toward Asia, pushing sun-baked surface water westward. As this warm water pools near Indonesia, deep, cold, nutrient-rich water is pulled up to the surface to replace it. This upwelling sustains South America's vast marine ecosystems. But every 2 to 7 years, the planetary pendulum swings back. For reasons scientists are still mapping out, those vital, steady trade winds weaken, and sometimes even reverse. When the wind stops holding that water in place, a localized failure in the Pacific sets off a global chain reaction. Without the trade winds pressing against it, gravity takes over. That massive pool of warm water built up in the Western Pacific begins to slosh backward, moving east toward the Americas. This satellite temperature map shows that eastward surge of heat. Forecasters specifically look at the bright pink and right anomalies pooling in the center and right side of the map, an area they call the Niño 3.4 region. As this deep layer of warm water reaches the eastern Pacific, it acts like a giant physical cap. It pushes down the thermal boundary layer of the ocean, the thermocline, and completely shuts off the upward flow of cold water. Stripped of cold, nutrient-rich water, the microscopic phytoplankton at the base of the food web die off. Fish populations plummet, and massive industries, like the Peruvian anchoveta fishery, one of the largest in the world, suddenly find their nets empty. The starvation of microscopic plants off the South American coast is the first domino falling on the path to disrupting the entire global economy. This animation illustrates how the atmosphere reacts to the warming ocean. The massive loop of air circulating over the equator, known as the Walker circulation, detaches from its usual position and shifts eastward, following the heat. Because the Pacific Basin spans a third of the Earth, moving that much heat and moisture physically reroutes the planet's upper-level jet streams and storm tracks. Moist air rises over the newly warmed eastern waters, generating heavy, persistent rain clouds. These storms inundate typically arid deserts in Peru and bring severe flooding and landslides to the southern United States. Meanwhile, the western Pacific is robbed of its usual rainfall. Countries like Indonesia and Australia plunge into crippling droughts, turning rainforests and brushlands into tinderboxes for choking, widespread fires. The atmospheric ripple effect is so immense that the altered winds even reach the Atlantic basin, slicing the tops off forming hurricanes before they can organize. A few degrees of warming in a targeted stretch of the Pacific Ocean is enough to completely rewire the weather of the entire planet. El Niño is a natural, repeating oscillation, but when you overlay its immense release of oceanic heat onto a planet already warmed by human-driven climate change, you get record-breaking temperature extremes. The compounding thermal stress triggers a wave of devastation. Global crop yields falter, wildfire seasons extend, and fragile marine ecosystems suffer through mass bleaching events as the water becomes simply too hot for corals to survive. We cannot stop the Pacific pendulum from swinging, but thanks to a dedicated coalition of global scientific organizations, we are no longer caught completely off guard. Researchers deploy a sprawling network of sensors, using orbital satellites and deep-sea Argo floats to actively monitor the water column, scanning for the earliest signs of the ocean beginning to slosh backward. Transforming El Niño into a highly predictable forecast allows humanity to bridge the gap between observation and action, providing the lead time necessary to survive the pendulum's next swing.